Welcome to the final section in our unit on electric charge and electric field. In this section, we're going to do a couple more examples of electric field calculations. The first one we're going to do involves a positive 3 coulomb and a negative 2 coulomb charge separated by 2 meters, and we want to know the electric field halfway in between them. Watch out for the negative sign. I see it is over here and got separated from the 2, so don't lose it. So let's let the 3 coulomb charge be here, the negative 2 coulomb charge be there. We know that the total distance between them is 2 meters, which means that the halfway point is 1 meter from each charge. Begin by thinking about direction. Electric field lines point out of positives, therefore the field due to the 3 coulomb will be to the right. They point into negatives, therefore the field due to the negative 2 coulomb will also be to the right. Therefore, the magnitudes of these two fields will add together. And I'm going to let positive be to the right in this problem. I can calculate the field due to the 3 coulomb charge, kq over r squared. K is 9 times 10 to the 9th Newton meters squared per coulomb squared, times 3 coulomb. R in this case is 1 meter. I got to square that too. And that calculates out to be 2.97 times 10 to the 10th newtons per coulomb. The field due to the negative 2 coulomb will be kq over r squared, which is 9 times 10 to the 9th Newton meters squared per coulomb squared, times 2 coulomb, notice the absolute value again, divided by 1 meter squared. And if you multiply that out, you get 1.8 times 10 to the 10th newtons per coulomb. I can now find the total field by adding, oh, that's supposed to be an equal sign. Okay, I can find the total field by adding the 3 coulomb field to the negative 2 coulomb field. Everything here was in the positive x, so I can add them together to get 2.97 times 10 to the 10th newtons per coulomb plus 1.8 times 10 to the 10th newtons per coulomb. I'm going to make a little note to me over here that this is all going to be in the positive x direction, and that works out to be 4.77 times 10 to the 10th newtons per coulomb. And I have found the magnitude and direction of the total field in between these two charges. In the next example, we're going to work with a slightly more complex geometry. Here I have a 2 coulomb and a negative 3 coulomb charge positioned on the vertices of a triangle. I see that the triangle has side length of 0.5 meters, and I want to know what is the electric field at the last corner, the third corner, so here. I'm again going to begin with looking at directions. Field points out of positives, therefore the field due to the 2 coulomb charge will point downward, and the field due to the negative 3 coulomb charge will point to the right because it is negative, therefore the field line will point in. In this case, I have to define a 2-dimensional coordinate system, so I'm going to let up positive for the y direction and to the right positive for x. And now I'm going to find the individual magnitudes. So the field due to the negative 3 coulomb will be k times 3 coulombs divided by r squared, which in this case is 0.5 meters. And when you multiply that out, you get 1.08 times 10 to the 11th newtons per coulomb. The field due to the 2 coulomb charge will be k times 2 coulombs divided by 0.5 meters squared. And that works out to be 7.2 times 10 to the 10th newtons per coulomb. The total field will again be the sum of the 3 coulomb and the negative 3 coulomb and the 2 coulomb fields. But since they're not in the same direction, I can't just add or subtract those two numbers. Instead, I have to think about what's going on and use Pythagorean theorem and trig. So the field due to the negative 3 coulomb pointed in the positive x direction. The field due to the 2 coulomb pointed downward. Therefore, the total field points along the diagonal. I'm going to define this angle relative to the x-axis, but below it as theta. And now I can find the magnitude of the total electric field using Pythagorean theorem. Because that is a 90-degree angle, since negative 3 is parallel to the x-axis and the 2 coulomb field is parallel to the y-axis, resulting in a magnitude of Nope, I wrote that wrong. Forgive me, I was looking at the wrong spot on my paper. That results in a magnitude of 1.29 times 10 to the 11th newtons per coulomb. And I can use trig. Tangent of theta is E2 over E negative 3, and that results in an angle of 33.7 degrees. So now I know the magnitude and direction of the electric field at the third point of the triangle. If I go back to the triangle, what this is telling me is that the total electric field is going to point something like this, 33.7 degrees. Okay. Now, bringing our discussion of the electric field back full circle, I now am going to place a 2 coulomb charge at that third corner. And that is not supposed to be a 2 coulomb charge, forgive me. It is supposed to be a 0.2 coulomb charge. So we're going to make that adjustment. And I want to know the force on that charge. Well, remember when I first introduced electric field, I wrote down a formula that said F equals QE, where E was caused by the surrounding charges or the source charges, and this guy was the other charge. Okay, well, the 2 coulomb is a source charge, the negative 3 coulomb is a source charge, and the 0.2 is the other charge, which we also referred to as a test charge. Okay. So if I want to find that force, I can find its magnitude by taking 0.2 coulombs and multiplying by the field that we just calculated of 1.29 times 10 to the 11th newtons per coulomb. And that gives me a magnitude of 2.58 times 10 to the 10th newtons. The direction will be along the electric field line. And so since the electric field line is coming down like this at a 33.7 degree angle, then the force will also be at that 33.7 degree angle below the x-axis. Oh, I can't spell here, below x-axis. Okay, well, one more what if, and then we will finish up this section. And that one more what if is, what if the charge placed there was negative? And again, please make it 0.2 instead of 2. Okay, well, remember the field line is going down like this. And this is that 33.7 degree angle. But as we've seen throughout our discussion of electric field, negative charges don't move along field lines, they move opposite. So the force is going to be this way. Okay, well, from the positive x-axis, we need this angle, and that is not so badly found. If this is 33.7, then this angle is 33.7, which means this angle, which I'm going to call phi, is going to be 180 degrees minus 33.7 degrees, which works out to be 146.3 degrees. And I'm just going to say that is from the positive x-axis, as angles are normally defined. So we've got the direction of the force. The magnitude of the force will again be found with F equals QE, and I'm going to absolute value this guy in this case because I don't want that negative sign to screw up my direction. I already know what direction the force is in. So that's going to be 0.2 coulombs times, again, 1.29 times 10 to the 11th newtons per coulomb, which works out to the exact same magnitude we had in the last what if of 2.58 times 10 to the 10th newtons. And again, this is going to be at 146.3 degrees from positive x-axis. This concludes this section. It also concludes this unit on electric charge, force, and field.